Hi everyone, welcome to this workshop. Zhi Cai, a PhD student from National University of Singapore. I'm advised by Jonathan Scarlett. I'm going to present the use of information theory techniques in showing the lower bounds of kernelized bandit problems. We are particularly interested in two problems. The first is called Bayesian optimization, where the goal is to find the maximum of a function based on black box queries. We are interested in functions belonging to an architecture's with bounded norm, and we also consider cases where the observation may be corrupted by independent Gaussian noises. After T steps, we measure the performance of the algorithm using the simple regret, which is simply the difference between the function optimum and our latest observed function value. So this is Bayesian optimization, and the other one is called Bayesian quadrature, which is basically estimating the integration of the target function through bandit feedbacks. The error measurement is just the mean absolute error between the true integral I and estimated integral I hat. As you may find that BO is more like estimating the L infinity norm of the function, and BQ is like estimating the L2 norm of the function. In this slide, we will only consider the Matin kernel functions with parameter nu, since Matin functions can have bounded support, whereas some other kernels like Gaussian kernel, the functions could have a very long tail, which brings certain amount of difficulty in showing the lower bound. All right, we now give some lower bound results in BO and BQ. For noiseless BO, we can construct a class of bound functions where each of them has disjoint supports. And by controlling the architecture norm of each function, we can control how many functions we can actually fail them in the domain. So if the number of functions is m, then with less than half of m queries, we can never distinguish at least half of the functions correctly. The error is then just the height of the constructed function, epsilon. So with this function class and the similar sort of techniques, we can extend this result to the noisy setting. In the noiseless setting, we are free to enjoy that with a single or a constant times of arm pulling in each region. It will suffice for the player to tell at least the difference between a bump and a zero function. However, this is not the case in the noisy setting because of noise. Fortunately, Fano's inequality can be used to decide the number of samples, say tau, needed within each bump, and this quantity is related to the KL divergence between two Gaussian distributions having the same variance sigma squared, but the gap in the Gaussian mean is epsilon. So finally, the overall query step is at least tau times the noiseless t. All right, so here we show another interesting viewpoint of the lower bound of the noise SBO by a recent paper using packing and covering number theory. And we want to show that there exists at least two architecture functions such that their distance is at least epsilon. In this paper, the authors show that to satisfy this property, the number of samples needed is related to the covering number of the function class, which is the number of functions that we can cover the domain. This actually shares a similar viewpoint as our previous method, where we have sliced the domain equally to fit all these functions. Another related problem is Bayesian quadrature. For the lower bound, we now make use of a slight different function class, where each function has m bumps, being positive or negative with half probability. Now with a budget of t less than half of m, the expectation of the estimation is 0. The error is then the variance of the estimation, which can be dealt with several approaches. Simple and elegant approaches to use Kinchen's inequality to directly obtain the lower bound of the expectation of the squared random variable. Another approach is to use the law of large numbers to consider sufficiently large m, then the distribution of the above summation will be asymptotically Gaussian, and an average absolute error proportional to the standard deviation is unavoidable. The extension from noiseless BQ to noisy BQ is pretty easy, since the noise term can be dealt separately with the noiseless term. The idea is to simply consider constant functions. So then the problem is now reduced to normal mean estimation, so that we can use the information-theoretic lower bound techniques introduced in the noisy BO proof. So then the final lower bound of the noisy BQ is just the combination of these two lower bounds. All right, this is all for this talk, and thank you for listening.